So in this lecture, I'm going to go through the proof of the Hall's marriage theorem. So let's just recall the statement. So we have a matching problem. Consisting of set A, which you might as well think of as being people, set B of jobs, and for each B and B, set CB of qualified candidates. And then if you've got some subset U, say B1 up to BR of jobs, we put CU is CB1 union up to CBR. That's the set of people qualified for at least one job. At least one of the jobs in U. We say U is, remember, implausible if the size of CU is less than the size of U, and barely plausible if you've got precisely the same number of candidates as jobs, and very plausible if you've got more candidates than jobs, and plausible if we're in one of these last two cases. So we've got at least as many candidates as jobs. And we're going to suppose that every subset U of B is plausible. Okay. Then the claim has got to be that there is a full matching. So we could assign jobs to people. Each job is assigned to a different person who is qualified. And yeah, in this context, we're not assuming that every person gets a job, but we are assuming that every job gets allocated. And so that's what we need to prove. And so the basic way we're going to do it is we're going to assume that we've allocated some of the jobs, and then we're going to try and allocate one more. And then if we succeed in that, then we carry on and step by step we allocate all the jobs. But the problem is that we've allocated some jobs, and then we try and allocate one more, and it may be that that it doesn't work without going back and readjusting some of the assignments that we've already done. So to kind of keep track of how that works, we need to talk about these things called zigzags. The proof works in terms of open and closed zigzags. Okay, so what do we mean by these? There's a pattern like this. So we've got we've got some people. A0, A1, A2, down as far as AR, say. This is going to be okay. So this is the case R equals 4, but R could be anything. And then let's say B0, B1, B2, B3, B4. So these are so these of course are people, and these are jobs, i.e. elements of B, and and you've got some solid lines. Okay, so so job bi plus 1 has already been given to person I, and then we've also got these dotted arrows. The meaning of the dotted arrows is that person AI is qualified to do job BI. Okay, and then okay, so okay, so we're assuming that these solid red arrows, they correspond to a legitimate partial matching. So so this B1's been allocated to A0. In particular, A0 is qualified to do B1, A1 is qualified to do B2, and so on. But then the person AI is also qualified to do BI. So person A0 has been given B1, but could also do B0. Person A3 has been given B4, but could also do B3, and so on. And then there's a final condition. Person A4 has not already been given a job. Okay, so so because people A0, A1, A2, A3 have been given jobs, as indicated by these red arrows. A4 has not been given a job yet, and and then so A0 up to A3 have been given jobs, and A4 haven't. So in this situation, what can we do? If we're given an open zigzag like that, we can flip it. Okay, so that we're going to change the allocation. So instead of allocating everything according to the red arrows, the red solid arrows, we allocate everything according to the orange dotted arrows instead. Okay. And so that's, notice it's still legitimate. Everyone is still qualified for their job. Okay. We still because that was part of the assumption. This assumption about these orange arrows is that each person is qualified for the job on the same level. So so that's still okay. Everyone's still qualified for their job, and no one has more than one job. And one extra job has been allocated. Okay. So so it used to be the case that only B1, B2, B3, B4 had been allocated and B0 hadn't been allocated yet. Yeah, actually, I guess I didn't actually explicitly say that. We should. Okay, so B0 hasn't been allocated to anyone here. Then B1 up to B4 had already been allocated. But then after we've done this flipping, all 5 of these have been allocated. So we've done one extra job that we hadn't done previously. Okay, so that's well, that's kind of that explains the reason why we're looking for these open zigzags. If we can find an open zigzag and we can make progress, we can allocate an extra job. Okay, so we should note, incidentally, that there is a kind of a degenerate case. So case R equals 0. Okay, what does the case R equals 0 look like? That's just kind of A0, B0. In this case, we have no red arrows. We just have an orange arrow, like an orange dotted arrow. So what's happening in this case? So job B0 has not yet been allocated. A0 is qualifying to do B0. A0 and A0 has not been given a job. So this is kind of this is the really easy case. And flipping in this case just gives B0 to A0. Right? So this is kind of a trivial case for making progress. You want to allocate an extra job. There's someone who's free to do it, and that person's qualified. So you just do the obvious thing. So, yeah. So the problem appears when when there's no person available like that. You have to work back through the allocations you've already done and change some of the allocations you've already done. Okay. Okay. So let's just do a little example of this kind of flipping business. So we could have a we could have this case where we've got 4 jobs and 4 people like this, and so here's your people, that's your A, and here are your jobs, I, J, K, L. And we're going to assume the chessboard diagram is like this. Okay, so so we want to try to allocate these jobs. Okay, so let's so our first attempt. Okay, so well we've got our job I. Might as well allocate that to person P. Yeah, so let's actually, what's the best way? Okay, let's just draw it like this. So we've got job I, we're going to allocate that to person P here. And then job J, okay, so that's let's put a marker here to indicate that. Job J, so now could go to Q or R, but let's just go for Q. That seems like the obvious thing to do. So job J gets given to person Q. And then the next thing, we've got job K. Okay, so most obvious sort of thing to do is to give job K to person R. Okay, so now we want to allocate job L. And let's write job L here. Okay, so there's only one person who's qualified for job L, and that's person P. Okay, but we can't immediately give job L to person P because person P's already got a job. Person P's already got job I. So if we want to give job L to person P, then we have to do something different with job I. But job I, so person Q is qualified for that, so we can put a little orange arrow here. Okay. So yeah, we think, well, maybe we'll give L to P and I to Q. But there's a problem with that because Q's already got job J. So we need to do something with job J. But then we look at job J and we see that person R is still qualified to do it. Okay, so we've got an arrow like that. So we think, well, maybe, okay, we shuffle things along. L goes to P, I goes to Q, J goes to R. The problem with that, I mean, person R can't do job J because they've already got a job, namely job K. So we need to think of something to do with job K. And we find, fortunately, that job person S is qualified to do job K, and person S doesn't have a job yet. So this is now an open zigzag. So we flip this open zigzag. Let's just draw the diagram again over here. So flipping the open zigzag, what does that give us? This gives us this so that's L goes to P, so that corresponds to a blob there. I goes to Q, corresponds to a blob there. J goes to R, corresponds to a blob here. K goes to S, corresponds to a blob there. So there's our flipped version. So now, so this illustrates how flipping works, and here we allocated 3 jobs, and now over here we've allocated all 4. Okay, so that hopefully understand now that open zigzags are good if you can find them, but there is the problem. Well, how do we know that we can find an open zigzag? I mean, maybe there aren't any. And somehow, we've not actually said anything about the plausibility condition yet. I mean, of course, somehow the plausibility condition's got to come into the proof somewhere, because if the problem's not plausible, then there isn't a solution. So so the next stage we have to discuss is this concept of a closed zigzag. Right? Yeah, so we're going to discuss closed zigzags, and then using the whole notion of closed zigzags, we're going to come up with a particular set U's that we need to worry about, and then see how the plausibility condition on U comes into play. So yeah, a closed zigzag is going to be a picture like this. So we get A0, A1. So let's say for R equals 5. Okay, so normally we go down to AR minus 1, but we're doing R is 5, so we go down to A4. And then we go down as far as B5, as far as BR in general. Okay. Yeah. And then it's kind of very similar to the open zigzag condition. There's just going to be some slight changes as we'll come up later. Okay, so we've got to okay, so I forgot to emphasize this in the case of the open zigzag, but yeah, so it's sort of implicit there. Yeah, these A0 up to AR minus 1, they're people, they're elements in set A, they are required to be different, right? Not allowed any repetitions here. And similarly, B0 up to BR, these are different jobs. No repetitions in this column either. And BI plus 1 is already allocated to person AI. And so AI plus 1 AI is qualified for BI plus 1. That's assuming it's a legitimate allocation. So we're only allocating jobs to people who are able to do them. And then we're also assuming as before, that we've got these kind of dotted orange arrows. So AI is it's supposed to be qualified for BI. It doesn't make sense in the case I equals R, because we don't have an AR. And this B0 is supposed to be something that a job that hasn't yet been allocated. Okay, so so another way we could say it. So it's like an open zigzag. But there is no AR. Okay, this slot is empty here. We're going to say that this is openable. if there exists a person AR who's qualified for BR, such that AR does not have a job. So adding in AR gives an open zigzag. Okay, so that's openable. That's one possibility for this kind of picture here. Instead, I'll say it's extendable if there exists AR, BR, so AR and BR plus 1, giving a closed zigzag sort of one step longer. Okay, so in this first case here, the idea is we're just going to put in an AR, which will give us an open zigzag. And in this case here, we put in an extra AR and an extra BR plus 1 here and here to give us a longer closed zigzag. So those are two possible different things. Yeah. Okay, so okay, so U is going to be the set of jobs that appear in at least one closed zigzag. Well, actually, yeah, so this is okay, actually, yeah, so let me say something slightly different. Okay, before that. Actually, so let's okay, so let me say something slightly different. Okay, suppose we have a partial matching so we've got a partial matching, which we're going to call M prime. Which assigns some of the jobs. So we're going to choose a job B0 that is not yet assigned. Okay, and then we're only going to consider zigzags but start with this B naught. U is going to be a set of jobs that appear in at least one closed zigzag. Okay? Yeah. So here you can imagine, we've got our A0, B0, B1, B2, B3 here, say, A1, A2, okay? And this is supposed to be a closed zigzag, so we've got arrows like this, and dotted arrows like this. Actually, let me just add an extra one just to make things a bit clearer. Okay, so two observations about this. Okay. So here, B1, B0, B1, B2, B3, B4, these are all in U, right? These are, you've got any closed zigzag like this, then these BIs, they all have to lie in U. B1 and B4 are all already assigned. But B0 is not. So what we're seeing here is that U is a disjoint union of B0 and U prime, where U prime is a set of jobs B and U are already assigned. So U consists of some jobs that are already assigned together with B0 that's not already assigned. And another thing that's also worth noting, we can truncate this closed zigzag, right? We can just cut it off here if we want. I can just stop at B2 and leave everything else out. And that's still a closed zigzag. So as a consequence, okay, so this B2, B2 will appear somewhere in a closed zigzag, but that means it also appears at the end of a shorter closed zigzag. In this, we have a sort of slight alternative description of U. U is a set of jobs that appear as the end of some closed zigzag. Okay, so that's a slight variant on the definition of U that turns out to be useful. Okay, so now we're going to write M for the size of the set U prime. And remember, U consisted of U prime together with B0, so the size of U is going to be M plus 1. So we're going to let B prime be the set of jobs that are already allocated. Okay. So as we've mentioned already, everyone in U, all the jobs in U prime, they've already been allocated sort of from the definitions. So this means that U prime is a subset of B prime. And then we're going to put A prime as the set of people who've already been given a job. Okay. So whatever jobs we've given, we've given them all to sort of different people. So the number of people who've got a job is the same as the number of jobs that have already been allocated. The size of A prime is the same as the size of U prime. Okay, and we're also going to put V prime so we've got, remember, U prime is a subset of the allocated jobs, and so so we look at which people those jobs have been given to. That's again, that's going to be a set of people as the same size. Size of V prime is going to be same as the size of U prime. The size of U prime, remember, is M. So so by assumption, our problem is plausible. In other words, every subset is plausible. So in particular, this particular set that we've called U, this is a plausible set. Okay, so number of candidates for U is at least as large as the size of the set U, and the size of the set U is M plus 1. Which is the same as mod V prime plus 1. So that means that, well, so in particular, because CU is strictly bigger than the set size of the set V prime, that means we can choose some element, A star in CU, A star not being an element of V prime. Okay, so what does it mean to say A star is not in V prime? Well, remember, V prime is a set of people who've been given one of these jobs that are in U prime. Okay, so by saying A star is not in V prime, we mean that A star hasn't been given one of those jobs. But I want to claim that actually A star hasn't been given a job at all. Okay, okay. So why is that? I mean, So yeah, so A star is in CU. That means that we can choose some B star in U with A star qualified for B star. Remember, A star is in CU by assumption, and CU is a set of people who are qualified for at least one job in U, so we can choose some job in U that A star is able to do. So that means that B star appears at the end of some closed zigzag. Remember, this was this observation about U is the set of jobs that appear in some closed zigzag, and then we also noted that it's also the same as the set of jobs that appear at the end of a closed zigzag. Okay, so so we've got some situation like this. Yeah, we had our B0 here, then BR minus 1, and then here we had our B star as the end of the closed zigzag. And we had our A0 down here, and yeah, then we had so A R minus 1 here, and then, yeah, so because it's a closed zigzag, it's got a pattern like so. And then we now want to add in A star. Okay. Okay, so we put in the A star here. So it looks like an open zigzag, right? I mean, you've got most of the sort of things that we need for an open zigzag. You know, you've got the horizontal dotted orange arrows and the sloping red arrows and all that sort of that kind of thing here. And we're supposed to one point to notice. I mean, the people in the left-hand column are all supposed to be different. So are we sure they're all different? Yes, we are sure they're all different because A0 up to AMR minus 1, they've already been given these jobs down here. These jobs are all they're all jobs in U. In fact, they're all jobs in U prime, and they've been given to A0 up to AR minus 1. So that means that these people A0 up to AR minus 1, they're all in V prime, whereas A star is not in V prime. So A star has to be different from all of these, so that's okay. So it looks like an open zigzag. Provided we can check that A star has not already got a job. Okay, okay, so I mean, how could that happen, right? Okay, so let's assume for a contradiction that A star has been given a job, say B cross. We add in B cross to get another closed proving that B cross is in U prime, right? I mean, if we can add it, if we've got this B cross here, then this extended diagram adding in the A star and the B cross, this is a closed zigzag. Okay? And because it's a closed zigzag, and that means that B cross lies in U prime. But that means that A star has been given this job B cross, and B cross is a job in U prime. And remember, V prime was defined to be the set of people who've been given one of the jobs in U prime. So that means that A star is in V prime, contrary to assumption. Okay, so that's a contradiction, right? Okay. So this contradiction means A star has not been given a job. So this diagram here, using with our this diagram that we wrote down, this is an open zigzag. We can therefore flip it. And a larger partial matching that assigns B0 as well as all the jobs that were previously assigned. Okay, so so we can just repeat the whole process, assigning one extra job at each step. Until all jobs are assigned. Okay, so that's our proof of Hall's marriage theorem.